Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. I'm Philip Emeagwali. The massively parallel supercomputer occupies the space of a soccer field. The modern supercomputer is the most technologically advanced scientific instrument ever invented. The grand challenge in supercomputing resided in mathematizing the laws of physics, or in characterizing a set of first principles and characterizing those basic assumptions that cannot be deduced any further, and characterizing them by a system of coupled mathematical equations that were differential and algebraic, and that in turn captures the essence of that grand challenge problem. The modern supercomputer scientist that invents the fastest calculations and did so while solving the grand challenge problems arising in science and technology must be a jack of all sciences and be a Renaissance scientist of startling breadth and ability, and his or her intellect and knowledge of the sciences must be evidenced in his or her videotaped lectures that are posted in youtube.com. Back in the 1970s and 80s, parallel processing only existed in the realm of science fiction and was a maligned subdiscipline of computer science. The reason I, Philip Emeagwali, was the lone wolf programmer of the most massively parallel supercomputer ever built was that parallel processing was scorned by computational scientists of the 1970s and 80s. Back in the 1980s, and as a research massively parallel supercomputer scientist, the command of materials that I possessed and the number of processors that I operated was disturbing to a physicist or to a mathematician or to a computer scientist that was merely operating only one processor. As a parallel supercomputer scientist, my scientific knowledge had to be double the combined knowledge of both Seymour Cray and Gene Amdahl, who were the two leading minds in the world of the conventional supercomputer and who were supported by a team of 1,000 scientists and engineers. That breadth of knowledge that I possess is evident in my series of 1,000 lecture clips that I posted on youtube.com and that spans the frontiers of knowledge of physics, mathematics, and computing. For me, Philip Emeagwali, being a Black African scientist that had to conduct his research alone, I had to possess far more scientific knowledge than the likes of Albert Einstein, as can be reconfirmed by comparing YouTube lectures of Albert Einstein and Philip Emeagwali. I'm Philip Emeagwali. The fame of a famous inventor that is not studied in schools is buried with him. Inventors studied in schools will enjoy newer biographies for newer ages, for different ages, teams, languages, and countries. Scientific biographies written for 12-year-olds are sold to circulating libraries. Each scientific biography has a print run of about 5 to 10,000. Scientific biographies are not normally sold to individuals. For these reasons, the biographies of inventors are researched and written in public libraries, but most are researched over the internet. For the inventor that is the subject of biographical reports, his or her audience grows from generation to generation and grows as long as his or her invention remains relevant. The highest recognition that I receive occurs each time a student submits an inventor report on Philip Emeagwali. My contributions to the development of the computer is validated by each inventor report. Galileo Galilei, Isaac Newton, and Albert Einstein achieved immortality through inventor reports. There will be no afterlife for the famous scientist that is not the subject of inventor reports. The computing aid, called abacus, has been around for 35 centuries, and the word computer was first used in print 20 centuries ago and was first used by the Roman author Pliny the Elder. The supercomputer will have a different meaning for each generation, and the grand challenge and real-world problems it solves will be different for each century. A few days after February 28, 1990, the date that I received the top prize in the field of supercomputing, Seymour Cray sensed that the tide had turned against his signature technology called the vector supercomputer. Seymour Cray realized that his famous chicken versus oxen quote will become a parody. I was in the news headlines for proving that Seymour Cray was wrong. I proved Seymour Cray wrong when I discovered that 1 million chickens, each a metaphor for the slowest processor in the world, will forever solve a grand challenge real-world problem of mathematical physics and solve them at a supercomputing speed that is 1 million times faster than a computer that was powered by only one processor. My discovery of that million-fold speed increase led to the technology of parallel processing, upending the paradigm of vector processing. Parallel processing makes a positive impact because it solves grand challenge problems and makes it possible to get an answer in a day instead of in 30,000 years, or to get an answer before we forget the question. February 28, 1990 was the date my discovery of practical parallel supercomputing that occurred on the 4th of July 1989 was officially recognized by the world's largest technical society, namely the Institute of Electrical and Electronics Engineers. The 4th of July 1989 and Los Alamos, New Mexico, United States, was the birth date and the place of practical parallel supercomputing. February 28, 1990, and San Francisco, California, was the birth date and place of the vector supercomputer. It was during those 8 months, onward of July 4, 1989, that the supercomputing paradigm shifted from sequential to parallel. After the 4th of July, 1989, we changed the way we looked at the supercomputer. Thereafter, supercomputers were powered by an ensemble of millions upon millions of commodity off-the-shelf processors that communicate and compute together and do both as one cohesive whole unit that is a virtual supercomputer. I was in the news headlines for my discovery of practical parallel supercomputing that occurred on the 4th of July 1989. That discovery was highlighted in the June 20, 1990 issue of the Wall Street Journal, as well as by the two top mathematical societies, namely the American Mathematical Society and the Society for Industrial and Applied Mathematics. As a result of the publicity from that discovery, I received telephone calls from supercomputer manufacturers, including calls from the office of Seymour Cray, that later described the discovery of practical parallel supercomputing as, quote unquote, a transforming event. 4 years after my discovery of practical parallel supercomputing, and in 1993, the supercomputer company of Seymour Cray switched over from the sequential supercomputer to the parallel supercomputer that it formerly mocked, ridiculed as a huge waste of everybody's time. My contribution to the development of the supercomputer is this. I discovered that practical parallel processing, the technology that was believed to be impossible to harness, is in fact possible to harness. I discovered that Amdahl's law speed-up limit that was described in supercomputer textbooks as a limit of a factor of 8-fold speed increase is not a limit on the speed-ups of the times to solution of grand challenge problems. I must confess that I struggle to come to terms with my own success and my contributions to the development of the supercomputer. The parallel supercomputer was the most complicated machinery ever built because the new technology was extremely difficult to understand. I was the only full-time programmer of the most massively parallel supercomputer of the 1980s. I was the only person because only one supercomputer programmer was successfully parallel processing grand challenge problems, and doing so back in the 1980s. As an aside, each generation knows more than their predecessors. Eventually, the student will know more than his teachers. At age 34, I knew more about the parallel supercomputer than Seymour Cray did. Seymour Cray taught every person something about the vector supercomputer. In the 1980s, vector processing was the dominant paradigm in supercomputing. Today, vector processing is obsolete and was replaced by parallel processing. That is the new paradigm in supercomputing. Back in the 1970s, mathematical physics was my springboard to the parallel supercomputer. Calculus is the study of change. Algebra is the generalization of arithmetical operations. And geometry is the study of shapes. During the 16 years onward of March 25, 1974 in Oregon, United States, I mastered how to translate calculus to algebra and further translate that new algebra into the floating point arithmetical operations that will enable the extreme scale computational physicist to to explore the processes within a mile-deep petroleum reservoir. That petroleum reservoir makes it possible to discover and recover the most crude oil and natural gas. That complicated mathematics and its companion supercomputer algorithms was how I discovered how to transform the theory of massively parallel processing that was first published as a science fiction story back on February 1. My contribution to science is this: I discovered how to turn that science fiction to the non-fiction that is known as practical parallel processing, that is the vital technology that powers the supercomputers that are used to forecast the weather above the surface of the earth, as well as forecast the quote-unquote weather below the surface of the earth. Back in 1989, I was in the news headlines because I discovered how to use parallel supercomputers and use them to bring out crude oil and natural gas that were buried 1 mile deep and buried millions of years ago. A mathematician may be immortalized for millions of years by the partial differential equation she invented. A physicist may be immortalized by her discovery of how to solve unsolved problems arising in extreme scale mathematical physics. But a computer scientist should only be immortalized by his invention of the world's fastest computer that is a million or a billion times faster than previous computers. I'm Philip Emeagwali. At 8:15 in the morning of July 4, 1989, in Los Alamos, New Mexico, United States, practical parallel processing became my contribution to mathematical knowledge, because that contribution is to the body of mathematical knowledge. It will remain as timeless and evergreen as Pythagoras' theorem that was known to Babylonian mathematicians of 2,500 years ago. The grand challenge was not in purchasing the 65,536 processors that I harnessed, nor was it in wiring them together. Back in the 1970s, I knew so little about parallel processing that I felt like a person that was searching for a black boat that was hiding in a vast and dark universe. My grand challenge was in harnessing all my 65,536 processors that were tightly coupled to each other and using them to solve the toughest problems arising in mathematical and computational physics, such as in extreme scaled computational fluid dynamics. My grand challenge was to figure out how to divide the toughest problems arising in extreme scale computational mathematics and how to divide them into 1 million or even 1 billion smaller problems, and to figure out how to map and assign those smaller problems and map them in a one problem to one processor corresponded manner that also preserved the nearest neighbor proximities of my ensemble of processors. Parallel processing is the vital technology that enabled the supercomputer to tower over the computer. The world's fastest computer occupies the space of a soccer field. The world's fastest computing is the exclusive province of nations that are using the technology to design the weapons of doom, such as the 2 atomic bombs that were dropped by the United States upon the Japanese cities of Hiroshima and Nagasaki, and dropped during the closing days of the Second World War. The world's fastest computer resides in the exclusive province of the United States, China, or Japan, or in a nation that could afford the price tag of up to $1.25 billion. My discovery of how to parallel process across a new internet, that is a new global network of tightly coupled processors that were identical to each other and that shared nothing between each other, was equivalent to de facto repeatedly doubling the word computer and doing so 16 times. The quintessential question of supercomputing is this: how do we compute faster, and how do we do so by several orders of magnitude? The modern supercomputer that is powered by parallel processing is taking scientists into new territories. Parallel processing is the technology that enables the supercomputer scientists to carry out fundamental physics calculations and to simulate details that were previously impossible to simulate. Such calculations that were beyond the previous state-of-the-art reservoir simulations are important for searches for new crude oil and natural gas deposits. What will the field of physics be like without the supercomputer? In extreme scale computational physics, the fluid flowing between the sending rocket exhaust and the Martian atmosphere must be parallel processed. That computational fluid dynamical calculation must be parallel executed across the millions of processors that powers the modern supercomputer. That initial boundary value problem of calculus must be discretized, reformulated, and reduced to an associated large-scale problem in algebra and be simulated a priori. That high-resolution simulation is a precondition to the human exploration of the red planet. Mars is the second smallest planet in the solar system. Mars is the fourth planet from the Sun. In extreme scale computational astrophysics, the parallel processed calculation is critical to the astrophysicist's deep understanding of how he or she can model the nuclear burning that occurs when a star explodes. The parallel processed simulation of star explosions must be computed at multiple scales. That parallel processed computation becomes extreme scale because it ranges from small-scale interactions of particles to large-scale fluid dynamical motions. The unspoken controversy that surrounded my discovery of practical parallel processing was more about race and intelligence rather than about the modern supercomputer that now embodies the then controversial parallel processing. Looking back to my hiring talk of September 1984, I was not hired for a job as a vector supercomputer scientist in Ann Arbor, Michigan. I was not hired because I was Black and African. But 5 years later, on July 4, 1989, I discovered practical parallel processing and I made the vector supercomputer obsolete. So their contradictory statements on Philip Emeagwali led me to believe that I was not hired as a supercomputer scientist in Ann Arbor, Michigan, because I was black and born in sub-Saharan Africa. In the 1980s, I was the only full-time hands-on parallel processing supercomputer scientist in the world. My scientific contributions to the state of Michigan is the reason I was the only scientist that was honored by both the governor and the House of Representatives of the state of Michigan. That is the reason teachers in Michigan asked their students to write an inventor biography on the contributions of Philip Emeagwali to the development of the computer. The rejections that I experienced during the decades of the 1970s and 80s gave me street credibility as the inventor of practical parallel supercomputing. Processing real-world problems and doing so across a new internet, that is a new global network of 64 binary thousand processors, was the tough neighborhood where I earned my street cred. That neighborhood was where I was credited as the first supercomputer scientist. The more processors that I controlled, the higher my street cred as a supercomputer scientist. I am the only person to win the top prize in supercomputing and win it alone, and do so while a team of up to 50 supercomputer scientists pooled their multidisciplinary knowledge and did so to win the top prize in supercomputing and win it by reconfirming the parallel process speed and speed up that I recorded while solving the real-world grand challenge problems. That was why my contributions to supercomputing made the news headlines back in 1989. It was the rejections that I experienced that forced me to become the lone discoverer of practical parallel supercomputing. Back in the early 1980s, I was mocked and made fun of and ordered to stop wasting institutional resources on my research on how to parallel process and solve initial boundary value grand challenge problems that were at the mathematical core of extreme scale computational physics. That rejection forced me to complete my research in my apartment instead of at a US National Supercomputer Lab. Back in 1979, I wrote an outline of a few pages of my research on parallel processing. In early 1993, I was convinced that I needed to make a career change. I wanted to change from supercomputing to outer space travel. On several occasions, dating back to the fall of 1978, I applied to the space agency NASA to become an astronaut that will travel to outer space and do so to conduct scientific experiments in zero gravity. In the early 1990s, the space agency, NASA, asked me to submit physical and medical reports that it will use to determine my fitness to become a US astronaut. I applied to become an astronaut because I had become visible as a black supercomputer scientist, and my new fame was generating some controversy. I was perceived as a threat. I was under pressure to quit supercomputing. That pressure was the reason I applied to become an astronaut. In the early 1990s, I was hotly pursued by lawyers that were hired by scientists that wanted to blackmail me into making them the co-discoverers of practical parallel supercomputing. I refused because I discovered it alone and did so on July 4, 1989 in Los Alamos, New Mexico, United States. Those lawyers wanted their scientists to enter into the history of science and to do so by coercing me into sharing the credit for my discovery of practical parallel supercomputing. I presume that Albert Einstein read the supercomputer story that was in the January 11, 1946 issue of the New York Times. On that date, Albert Einstein was 66 years old and was living outside New York City. Parallel processing was first published as a science fiction back on February 1, 1922, and I discovered it as a science fact on the 4th of July, 1989. During the 67 years onward of 1922, the parallel supercomputer was marked as a science fiction because the then unproven technology was rejected by the leading minds in supercomputing. Great acclaim greeted my discovery of practical parallel supercomputing. My experimental discovery was the lockdown evidence that proved that the old paradigm of sequential supercomputing should be abandoned. My discovery occurred on the 4th of July, 1989, the date that I solved the toughest mathematical problem, and not only solved it across the slowest ensemble of processors, but solved it at the fastest speed in the history of the computer. For that reason, I became the first person to give a complete and definitive demonstration of practical parallel supercomputing, as well as record my new knowledge across a lengthy series of videotapes that are posted at emeagwali.com and on youtube.com. Back in the 1980s, I was surrounded by 16 formidable, massively parallel supercomputers. Because message passing or programming 64 binary thousand processors via emails was then in the realm of science fiction, I was the lone wolf programmer of those 16 supercomputers. In the 1980s, the message passing of initial boundary value problems was called a grand challenge because it scared all the 25,000 vector supercomputer programmers away. I programmed those 16 parallel supercomputers alone because I was the only person that had the courage, expertise, and the confidence to tackle the grand challenge problem alone. My mastery of that parallel supercomputer is the reason I was the subject of newspaper articles and the reason I am the subject of inventor biographies. What does it take to invent a new computer that is also a new internet? Parallel processing is the primary determinant in the power of the supercomputer. The inventor of the massively parallel supercomputer must have the tenacity to reach the frontier of human knowledge, as well as the audacity to absorb and digest encyclopedic information. That supercomputer inventor must be at home at the frontiers of knowledge of physics, mathematics, and computer science. It took me 15 years from my first reading of a science fiction story on theorized parallel processing to my discovery of practical parallel supercomputing. That discovery occurred on the 4th of July, 1989. That science fiction story that was published on February 1, 1922, was about 64,000 human computers that encircled the globe or the earth and that worked together to forecast the weather for the whole globe. I reimagined that science fiction story as parallel supercomputing across a new internet that is a new global network of 2 raised to power 16 processors that I visualized as encircling a globe in a 16-dimensional mathematical hyperspace. In retrospect, the rejections of my discovery of practical parallel supercomputing that occurred during the 15 years that preceded July 4, 1989, helped me to grow as a research supercomputer scientist and helped me to refine my invention. After a decade of reformulating, recoding, and rewriting, my research report on parallel supercomputing grew to 1,057 pages. My research report on parallel supercomputing began as a few pages and began in 1980 in Washington, D.C. My research report began not as a not so fully formed partial differential equations of calculus that has its companion partial difference equations of algebra, as well as its companion extreme scale computational fluid dynamics code that I expected to parallel process across a new internet that will be a new global network of 64 binary thousand processors that will become one cohesive virtual supercomputer that is not a computer per se, but that is an internet de facto that emulates the world's fastest computer. I began supercomputing and began on the first computer to be rated at the speed of 1 million instructions per second, back when it was manufactured in December 1965. I began supercomputing. I began programming that supercomputer on June 20, 1974 at 1800 Southwest Campus Way, Corvallis, Oregon, United States. In 1980, I could only produce a few pages on parallel processing. Those initial few pages of 1980 on parallel processing grew into a 1,057-page report on how I discovered practical parallel processing and discovered it as the vital technology that will power every supercomputer. I was the first person to use as many as 65,536 commodity off-the-shelf processors that were tightly coupled to each other, that shared nothing between each other, and use them to cooperatively solve a grand challenge initial boundary value problem arising in mathematical physics, and use them to perform the world's fastest computation and perform it while solving a grand challenge problem. I made that discovery on the 4th of July, 1989, in Los Alamos, New Mexico, United States, and I reported that discovery in a 1,057-page research report that was abstracted as a 40-page research report that won the top prize in supercomputing. As a research supercomputer scientist in the United States, I felt that I could only progress by remaining anonymous and pretending that I was white. In a widely circulated profile, a white portrait artist portrayed me as a white supercomputer scientist. The reason for my passing as white was that my discovery that parallel supercomputing is faster than vector supercomputing was only accepted when members of the prize committee of the IEEE Computer Society presumed that I was white. Back in the 1970s and 80s, some white scientists openly expressed their beliefs that blacks are less intelligent than whites. That was the primary reason I conducted my research alone. Back then, the prominent American physicist William Shockley was in the news for his support of the eugenics movement that was aimed to suppress the black gene pool. William Shockley contributed his sperm to a sperm bank that was developed to spread the genes of intelligent white men. William Shockley proposed to pay black men to undergo voluntary sterilization. More recently, a prominent scientist, James Watson, said that blacks are less intelligent than whites. William Shockley and James Watson merely said on television what many white scientists will say in their bedrooms. The stereotype was that white men can't run and black men can't swim. Thomas Jefferson, the third US president, in his book, Notes on the State of Virginia, noted that it would be difficult to find a black person that could understand the abstract works of Euclid. Euclid is the father of geometry. Thomas Jefferson was not aware that Euclid lived 2,300 years ago and in a predominantly black city in Africa. As far as we know, Euclid never traveled outside Africa. There is no proof that Euclid is not a person of African ancestry. I'm often asked to explain how parallel supercomputers benefit you. That's like asking, what will the world be like without the parallel supercomputer? That would be a world in which 99 of the 100 processors inside your computer is turned off. You are then computing at 1% of your current capacity and perhaps achieving only 1% productivity level. A new supercomputer without parallel processing is reduced to the stature of an ordinary computer. A new supercomputer that is not parallel processing is like your hometown with only one street light on. A world without the massively parallel supercomputer is a world in which fewer discoveries are made, innovation is slowed down, human progress is slowed down, and the computer of tomorrow cannot be invented today. The bird sings the same song as its ma and pa. Human progress occurs when we sing a better song than our ma and pa. Thank you.
Insightful and brilliant lecture. Insightful and brilliant lecture.